Welcome, and thank you for joining us. My name is Dean Lee, and I'm Professor of Physics at the Facility for Rare Isotope Beams, or FRIB. Today's public talk is part of an initiative at FRIB called the Advanced Studies Gateway. The goal of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all fields and strengthen ties between Michigan State University and the community. Today we have the pleasure of presenting a public lecture by Professor Michael Manfra from Purdue University entitled Quantum Mechanics, Identical Particles, and the Strange Case of Anyons. Professor Manfra is the Bill and D. O'Brien Distinguished Professor of Physics and Astronomy, Professor of Materials Engineering, and Professor of Electrical and Computer Engineering at Purdue University. He was born, raised, and educated in Boston, Massachusetts, where he received his bachelor's degree from Harvard in 1992, his PhD from Boston University in 1999. He then spent 2 years as a postdoctoral member of the technical staff at Bell Laboratories Lucent Technologies from 1998 to 2000, and in 2001 became a member of the technical staff of Bell Laboratories, where he conducted research in low-dimensional electron systems. After 10 years at Bell Labs, he moved to Purdue University in 2009. He was a Keck Foundation awardee in 2013. He was elected as a Fellow of the American Physical Society in 2015, and in 2016 became the Scientific Director of Microsoft Quantum Lab West Lafayette. In 2020, his group reported interferometric measurement of anion braiding, giving experimental evidence for a theoretical prediction made 40 years earlier. If you have any questions during this talk, please type them into the chat or the question and answer dialog box. At this time, it is my great pleasure to introduce Michael Manfra.
Okay, well, thanks, Dean. Thanks for that very flattering introduction. So I'm going to tell you today about something that I work on, but is also fairly general. So I think it'll be of interest to a broad community of interested people. And it has to do with some of the strangeness and funny rules that take place when we describe the microscopic world via quantum mechanics. And so this title of Quantum Mechanics, Identical Particles, and the Strange Case of Anyons is to entice you to think about some of the properties that when we describe the world quantum mechanically at the atomic scale, how they differ from our classical intuition. So hopefully everyone can hear me and things are clear. So let me advance the slides here. So there's the microscopic world of atoms and electrons moving and solids is described by quantum mechanics. And in quantum mechanics, we describe the state of a system. It can be a system of, say, many electrons moving around and conducting electricity in a solid by something called a wave function. And the wave function, psi, can be a function of many parameters, typically the positions of all the particles and time. And if you know the wave function and you know this other characteristic of a quantum mechanical system, it's Hamiltonian, which describes its energy spectrum and time evolution, you pretty much know everything there is to know about the quantum system. And one thing that is different from our classical world is this notion of identical particles and indistinguishability. At the in the microscopic level, we can't really, all electrons are the same. They're not distinguished by any internal degree of freedom or any property. And because of the uncertainty principle of quantum mechanics, we can't know position and momentum with infinite precision at the same time. particles can actually be indistinguishable. We can't tell the difference between an electron at position x1 and an electron at position x2. And therefore, the global properties can't really depend on what we call electron 1 or electron 2. And this is distinct from our classical intuition, where if we think of billiard balls on the pool table, all the pool balls may be identical in some sense, but we can certainly tell them apart. They're distinguishable. We can monitor their trajectory as they move across the table and bounce into other billiard balls. That's something we are comfortable with in classical physics, but mechanically, that notion really doesn't exist. So I'm going to use some equations, but please don't be concerned about the equations. You really don't have to know in detail what the equations mean to get the underlying physical principles. So when we say things are identical and indistinguishable, we mean that they cannot be distinguished by any quantum mechanical degree of freedom. So let's consider a wave function of just two particles, two electrons. And if we take the square of the electron wave function, that gives us the probability density for finding particles at a particular location, be it x1 or x2. Now, if we have a wave function that has just two particles and we exchange the position of those two particles, the amplitude squared, this probability of finding particles, clearly can't change. That would be unphysical. So it must be that when we exchange the position of particles, all we do to this wave function is introduce a phase factor. That's that e to the I alpha that you see in the equation, the first equation. I don't know if you can see my cursor. Maybe I need to turn this on. I'll put a laser pointer on. And I'm now pointing, hopefully you can see, that when we square the amplitude of the wave function in which we've exchanged particle 1, particle 2, at most we can build up a phase factor. That's that expression e to the I alpha. So we can use fancy language, but it really doesn't mean any more than I've already said. We can define an exchange operator. That operator acts on the wave function and it just exchanges the positions of the particle. And if we do that twice, what does your intuition tell you? Well, if we exchange the particles once and then we do it a second time, we must come back to the same state. We've just gone all the way back to where we started from. So therefore, applying the exchange or permutation operator twice must be the equivalent to the identity. It's the equivalent of doing nothing. So that tells us that this phase factor can only take on two specific values. It can either be a phase factor of pi or 2 pi. And for wave functions in which when we exchange the two particles, we get exactly the same wave function back, those are called bosons. And for wave functions where we pick up a phase factor of pi, that's equivalent to multiplying the wave function by a factor of -1. So I take the wave function, I exchange the two positions, and I get the same wave function back, but with a minus sign. Those are called fermions. And in nature, the fundamental particles of nature that we are aware of can only be bosons or fermions. That's the only thing you can get, at least in 3 spatial dimensions and 1 time dimension. And there's another property that I'll tell you about in a second, but whether a particle is a boson or a fermion is actually intimately tied to the spin of the particle. Now, the spin is an internal degree of freedom. We can think of it as a little, if you want to think of an electron as a little top spinning around, and that top can be pointing up or pointing down. And the physical manifestation is that it has a magnetic moment. It acts like a little magnet. So the spinning up is not equivalent to spinning down, but it's a completely internal degree of freedom. There's a deep connection between spin and these statistics that I'm telling you about, whether particles are fermions or bosons. So in quantum mechanics, all elementary particles are classified as bosons or fermions. And particles with half integer spin, again, you don't need to know the details, this is just a quantum mechanical degree of freedom, are fermions, and they have fermionic wave functions. That means they're antisymmetric under particle exchange. And all particles with integer spin, be it 1, 0, 2, are described by bosonic wave functions, and they are symmetric under exchange. And you may say that this is just sort of abstract mathematics and who cares, but it has profound influence on how these particles behave in the aggregate when we have lots of them together. If the fact that electrons, half-integer spin particles, are fermions, knowing this and that they obey the Pauli exclusion principle, that they don't like to be in the same quantum state, knowing that and a few symmetry arguments can go a long way towards explaining the properties, conduction properties of solids, be it metals, semiconductors, or insulators. In the lower left-hand panel, I show you what's something called the Fermi surface. It's just the energy distribution of electrons in copper wire that carries current in and out of your house. So knowing the fermionic statistics and symmetry allows you to understand why some materials are good conductors, some are semiconductors, and some are insulators. Conversely, the fact that integral spin particles like photons and certain atoms are bosons has profound impact as well. Bosons can be in the same quantum state at the same time. They like to flock together. And a dramatic manifestation of this is Bose-Einstein condensation, where all bosons at sufficiently low temperature can fall into the same state. And this gives rise to spectacular behaviors like superfluidity and superconductivity. So flowing without resistance and all being in the same quantum state is a unique property associated with being a boson. And so if, I go a little bit further, all elementary particles, and this was known essentially by the end of the 1920s, are fermions or bosons. And these dramatically different properties, when you have lots of bosons or fermions together, like I just described, is really important for describing the quantum mechanical behavior of systems. And so electrons, quarks, muons, neutrons, protons, many things that you've heard about in the subatomic world are fermions. Now, other particles are bosons. The Higgs bosons, gluons, photons, the particle of light are bosons. And as I said, fermions are antisocial. They obey the Pauli exclusion principle. They don't like each other and they try to stay out of each other's way. Bosons are very gregarious and social. They like to flock together and can all exist in the same state. Now, that was kind of it. Quantum mechanics by the early 1930s told us that there were fermions and bosons, and for about 100 years or so, that's what we thought could exist in nature. But actually, in the late 70s and early 80s, mathematical physicists started considering what could happen in reduced dimensional systems. Somehow, if we could remove some of the spatial dimensions, would that still be true? We could only have bosons and fermions. And it turns out that in low dimensional systems, say 2D, I'll explain how we have real 2D systems later, but you can have a particle that has very strange statistics. They're called anyons. This is a term that was first coined by Frank Wilczek in describing the unusual statistical properties of this. And they can have fractional charge, meaning we think that the fundamental charge in nature is that of the electron, and it's not divisible. That's an electron. All electrons have exactly the same quantized charge. But in low dimensional systems, you can actually have fractional charge, and you can have fractional statistics, braiding statistics. And what that means is that instead of only being a fermion or a boson and having this phase factor of 1 or -1, you can have complex phases develop associated with these wave functions. Dean, I believe there's a question, or should I be answering questions along the way, or? You're muted, Dean.
Yeah, there was a question. There was just a comment other than Cooper pairs with a smiley face. So it was just a comment.
Oh, okay. Oh, yeah, sorry. Anyway, so in low dimensional systems, you can have these really unprecedented quantum effects where the charge of the electron can be fractionalized. We can see objects behave as if they have 1/3 the charge of an electron. And their statistics are neither fermionic nor bosonic. They have fractional statistics. And one of the prime examples of this is in nature is a fractional quantum Hall effect that I'll describe to you in a bit. But this is the central idea that we can have particles in reduced dimensional systems that are neither fermions or bosons, and we call them anyons because they can have any statistics. It's kind of a joke that they interpolate between fermions and bosons. Moreover, anyons come in different flavors themselves. You can have abelian anyons where there's a phase that develops with the wave function, and those are the ones I'll describe mostly to you, but there are also examples of non-abelian anyons in which these exchange processes, where we change the coordinates of the particles, not only introduces a complex phase, but actually changes the state itself. These operations do not commute. And that generates a lot of interest because those types of states can potentially be used to store quantum information and be potentially used for quantum computation purposes. Okay, but we'll get there. So, and again, people should feel free if there's any questions or anything's unclear, please just interject and ask me a question. I'm happy to answer it. So this idea that there could be quantum mechanics of things that are not fermions or bosons goes back to some mathematical treatments in the late 70s by Linnaeus and Merham. But the quantum mechanics of fractional spin particles, and where the concept of the anyon was first defined, was in the work of Frank Wilczek back in the early 80s. And he considered a toy model. It seemed maybe a little unusual at the time, but it turned out to be pretty prescient to think of this, where he considered composite objects formed of a charged particle and a vortex. A vortex is just a circulation in the wave function. So if you create composite objects comprised of charged particles and vortices in 2+1 dimensional models, 2 spatial dimensions in one time, what Frank discovered was that the statistics of these objects, like their spin, interpolates continuously between the usual boson and fermion cases. And this was a toy model, a mathematical model, and he had a statement to that effect in the paper, but I think is interesting with hindsight. Although practical applications of these phenomena seem remote, I think they have considerable methodological interest and do shed light on the fundamental spin statistics connection. So again, these were just a construct at the time, but in 1982, the discovery of the fractional quantum Hall effect in 2-dimensional electron systems took place, and that's really spawned a lot of theoretical considerations. And in order to describe this phenomenon that I'll describe to you shortly, some very revolutionary new ideas had to be invoked. It couldn't be described by our normal reckoning of quantum mechanics and single particle physics. And one of the great leaps forward was the guessing by Robert Laughlin, or inspired guess I would call it, of the Laughlin wave function that describes the principal fractional quantum Hall effect states. It's a multi-particle wave function. One of the consequences of Laughlin's theory of the fractional quantum Hall effect is that the charge excitations, the particles in the system, must carry a fraction of the electron charge. At nu equals 1/3, the state I'll describe later. The charge is E/3. And this is a sharp quantum number. It's not like the charge is sort of, kind of around 1/3 of the electron charge. It's actually a sharp quantum number of the excitations of the system. So it's a very bizarre concept. You think I have an electron gas comprised of, say, 10 to the 11 electrons per square centimeter, and I put electrical leads on it, I measure the conduction properties of this collection of electrons, but the fundamental objects behave as if they're a fraction of an electron. That's pretty strange. Equally strange, and for me, equally interesting, was the notion that not only these particles would have fractional charge, but they would have fractional statistics. And this is originally noted in the work of Bert Halperin when he was trying to describe how to construct theoretically some of these fractional quantum Hall states. He noticed that in order to be self-consistent, that these excitations must have fractional statistics. And here's again, with hindsight, I think amusing statement. The fractional statistics here is strongly reminiscent of the fractional statistics introduced by Wilczek to describe charged particles tied to magnetic flux tubes in 2 dimensions. Now note the dates. This is November of '83. Frank Wilczek's paper was June of '82. This is all happening in rapid succession. And this notion that we should be considering charged particles tied to vortices or magnetic flux tubes the understanding of that only really came to the fore throughout the 80s and early 90s. This is actually the way we should be describing electrons, 2-dimensional electrons, at low temperatures in a strong magnetic field when they're strongly interacting. And this is actually the object we should be considering. But at the time, this were all revolutionary new ideas, and they were just being understood. Now, it didn't take too long for others, including Frank Wilczek and Schrieffer and Arovas, to also formulate that the quantum Hall effect, the fractional quantum Hall effect, naturally implies that the excitations have fractional charge and fractional statistics. So in the early 80s, there was this discovery of the fractional quantum Hall effect I'll describe, where it's seen in the transport properties, the electrical conduction properties of 2-dimensional electron systems at low temperature and high magnetic field. And there were these really rather unusual theoretical proposals put forth to describe the physical phenomenon that invoked fractionalization of charge and statistics. But it took quite some time for us experimentalists to actually devise and understand experiments that could probe these properties directly. And that's the story that I'd like to tell you a little bit about, how we went from a theoretical concept in the early 80s to realization, it's almost 40 years later. So that's the story we'll get into right now. So if I consider an electron just a single electron in 2 dimensions, meaning it's confined to a plane, I haven't told you how, but you just assume that it's possible, that the electron can only move along the tabletop and not perpendicular to the tabletop, and it's in a magnetic field. Now, you see some equations here. Don't worry about the equations. Basically, the statement is, for that problem, I can write down analytically the wave function for the single electron. That's that psi that I showed. Because it's Hamiltonian, that energy function that I told you about earlier is rather simple. It looks like it's slightly modified from the classical term, where you would have momentum squared over 2 times the mass as the kinetic energy. It's modified by the presence of the magnetic field. That's captured in this term called A here, which we call it is the vector potential. It just represents the magnetic field. But forgetting all the mathematics, what comes out is that this problem is actually equivalent to the harmonic oscillator. Everyone remembers the harmonic oscillator of a mass on a spring under small displacements. It turns out that the electron in a magnetic field quantum mechanically is a harmonic oscillator. So we can write down its energy. This is that harmonic oscillator energy E, described by a subscript n plus 1/2 h bar omega c is just the energy. And it has very simple wave functions that the psi right below. And if you think of it classically, if you think of a classical electron, you put in a magnetic field, it's just going to go in a circular orbit. If the magnetic field's pointing up and my electron can only move in the plane, it's just going to go circular motion. It's called cyclotron motion. We know that from classical physics. What I've plotted here is the probability density associated with the quantum mechanical wave function. And the white line with the arrows sort of shows you what the classical trajectory would be. The colors tell you the probability, how where you're most likely to find the electron. The red region is of high probability, the blue is region of low probability. And so for the lowest Landau level, n equals 0, and angular momentum 1, it kind of looks like a donut. It looks like a little donut. And so that circular orbit that we're talking about classically sort of gets smeared out a little bit, but it's the same idea. And if you're interested, if people are interested, there's lots of good introductory textbooks that I've listed here that you can learn more about it. Again, mathematics isn't crucial. Just the idea that if you put an electron in a perpendicular magnetic field, it'll undergo circular orbits, and we can write down the wave functions for those pretty simply. Now, things get more complicated if we have a bunch of electrons in the same 2D layer, and they're strongly interacting. Remember, electrons are charged, and they feel a repulsive interaction. So if you have many electrons in high magnetic field, that's the regime of the fractional quantum Hall effect. And that energy function, that Hamiltonian, still has this kinetic energy term, the one I just described to you, but it has another one that looks innocent enough, but is really causes all the interesting physics and problems in its solution. This is the mutual interaction of the electrons. They're all charged, and they interact strongly together. And that really is the determining factor in what determines the ground state of this system. Now, I want to emphasize, this is the real world. Samples are not perfect. They're samples that we make from semiconductors, and we put leads on them. Here's a picture of one of the original samples from Bell Labs from Stormer and Sui, and you can see the leads that are soldered on. All those blobs are just indium that's been annealed into the sample. It's a real mess, okay? It's an imperfect world. Yet the physics it gives rise to is universal. It doesn't depend on the details. That's what's really cool about it. Usually solid state physics, you have to worry about everything. The details really matter. In a few special cases, nature is kind to us and we get universal behavior. And the fractional quantum Hall effect is one such example. So despite the ugliness of this sample, it gives rise to very beautiful universal physics. And this is the original data where they measure the longitudinal resistance. That's just the resistance along the length of the sample as a function of magnetic field. It's at low temperature. And they measure the Hall resistance. That's the transverse resistance. Basically, the voltage that builds up across the sample as you drive a current along its length, but you have a perpendicular magnetic field. And what you see is that this magical number of 1/3, the filling factor 1/3, that just tells you the ratio of density of electrons to the number of flux quanta penetrating the system. The Hall resistance becomes quantized to a very precise value, and the longitudinal resistance drops to nearly 0. In fact, at low temperature and higher quality samples, it goes really to 0. So current flows as if without dissipation along the edge of the sample. And so as samples got better in time, this is some data from about 10 years later from Bell Labs, you see these very precisely quantized flat plateaus in the Hall resistance and real zeros of the longitudinal resistance. It's not superconductivity because there's a Hall voltage, but the resistance along the sample is dropping to 0. It's as if there's no backscattering. And this is the phenomenon that is of interest in where anions can exist. Now, this filling factor, as I said, describes the ratio of the basically density of electrons to the magnetic flux density in the system. How many flux quanta do we have? with the perpendicular magnetic field. And when it takes on integer values, 1, 2, 3, we get basically gaps in the energy spectrum. Remember those single particle levels that I described? There's gaps by h bar omega c. And so we can explain these integers using pretty simple concepts of single particle quantum mechanics. But you see that the phenomenology is kind of the same at certain fractional fillings that get 1/3. I only have I have 3 flux quanta for each electron available in my system. That's why I have the filling factor 1/3. Yet the transport properties, the Hall resistance and the longitudinal resistance, look just like in the integer case. And that was the real quandary, the thing that was very hard to explain, and took these more advanced concepts in order to understand. And that's what I'll try to show you a bit about now. So I'm going to show you something that may look like a scary equation, but don't worry.
Mike, while you are there, there is a question from Manfra. The second term of the Coulomb interaction seems to relate to Coulomb's law. The question is, what happened to Coulomb's constant?
Coulomb's constant. It is Coulomb's law. All the dielectric constant, if you mean all those dimensionful quantities, have been suppressed in the way I've written the Hamiltonian. This is what theorists like to do. So if everything has been set equal to 1, but there certainly the Coulomb interaction does behave in the solid state environment, but there is screening, and that is usually captured in the dielectric function of the material. So it's a good question. It's something I've kind of ignored the details of for this discussion. But of course, in reality, all those details matter and affect how the device functions. So thanks. I hope that helps. Mm-hmm. Okay. So the genius of Laughlin was to state that the fractional clump Hall effect, as first observed by Stormer and Stewie and Gossard at nu equals 1/3, is actually described by this multi-electron wave function, many particle wave function. And it has features associated with the single particle levels of a filled Landau level. But what really makes it work and makes it the unique solution is this Jastrow term where Laughlin has put 3 zeros at the position of each particle. So what this does is accommodates the Coulomb repulsion of the electrons. It really minimizes the overall energy, and we can create this wave function 1/3, and we can create excitations, which we call quasi-holes. This is the wave function with one quasi-hole placed at coordinate z0. This z coordinate is just a way of representing the in complex notation the xy plane. So z is the single complex coordinate, but it represents x plus iy. And we do have some physical constants that have been lumped into this magnetic length scale, which is the square root of Planck's constant divided by the charged electron times the magnetic field. That magnetic length basically sets the size of the little orbit. So remember that little circle I was drawing for you before? You can think of its extent as being related to this length scale, LB, that is called the magnetic length. But what we can do is we can write down these explicit wave functions and construct the excitations. And these excitations, which we call quasi-particles or quasi-holes, depending on whether we're adding or removing electrons from the system, can be written down in this way. And the consequences of Laughlin's, obviously I can't go into all the details here of the implications, but suffice it to say that the Laughlin's wave function and treatment necessarily tells us that the quasi-particles have a fractional charge. Okay, at 1/3, they carry 1/3 of the electron charge, and the arguments of Halperin, Wilczek, and Rovas and others tell us that they also have fractional statistics, that they're anions. Okay, so let's move forward to the modern day. And I know some of that math may look a little intimidating. It is, in fact, but the ideas are fairly easy to understand. So in the fractional quantum Hall regime, a two-dimensional electron gas, these electrons condense, if you will, into a Laughlin state, and that's the lowest energy state for them. And the excitations of this state, that when we try to drive a current or put some finite bias on it, are anions. They have fractional charge and fractional statistics. So the bulk experiment is quite simple. You just have this slab of material which contains a 2D gas, aluminum gallium arsenide in our case. You drive a current through it, you cool it down to near absolute zero, you apply a perpendicular magnetic field, and you monitor the resistance along the sample and across the sample. And here's some data on the right-hand side, taken last year in a modern dilution refrigerator. It's very cold. It's only 10 millikelvin, near absolute zero, and the samples have improved. And you see all these spikes, resistance spikes, and then regions where the resistance is zero and the Hall resistance is quantized. And it's quantized very precisely in units of E²/h, the fundamental charge of the electron, and Planck's constant. Even though this is happening in a dirty macroscopic sample, this Hall resistance is quantized to incredible precision. In fact, it is now the standard by which we define the ohm. The von Klitzing unit, after the person who discovered the integer effect, defines the standard of an ohm because it depends only on fundamental constants of nature. But that's for the integer state. For these fractional states like 2/3, 3/5, and 1/3 I'm going to talk about, those guys are more complicated and contain anions. And so the quasi-particles carry a fraction of the electron charge. Laughlin noted this in 1983. But what I want to tell you about, the interesting part for me, I'm an experimentalist, it wasn't until experimental techniques and samples improved about 15 years that two groups, one at the Weizmann Institute in Israel and one in Saclay in Paris, developed quantum shot noise techniques enough to actually measure the shot noise of these fractional charges. So even though Laughlin would say, well, it's obvious they're fractionally charged in 1983, it takes experimentalists some time to actually probe these things directly. And the part that I played a role in is that these braiding statistics were also known to the theorists early on, back in the 80s. But it took a long time, even longer, to try to find experiments that could look at that directly. And that's the story I'm telling you about. So just to be clear, in cartoon fashion, these excitations, these anions, are represented by these little spirals, okay, the vortex, if you will. And if I take one of these guys and wrap it around the other so that I come back to the original configuration, you'd say, well, that's stupid, that's boring, I'm back in the same state. But in truth, because of the quantum mechanical properties of anions, the wave function develops a non-trivial phase. And it's equal in this case to 2 pi, the ratio of the effective charge to the bare electron charge. So at nu equals 1/3, that statistical phase is 2 pi over 3. And we've, and many others have worked on this. Many groups, both theoretical and experimental groups, have devised means to probe that anionic phase as directly as we can. Okay, now, what I'm talking about are called, in the jargon of theoretical physics, abelian anions. There's even other types of anions, and they're called non-abelian anions, where these operations don't commute. And so there's an internal degree of freedom that must change when we exchange or braid particles around one another. And these non-abelian anions may have utility in storing and manipulating quantum information. I'm just going to give you a little flavor for that in cartoon fashion now, because this is something that you may hear about in the popular literature. So I'm going to show you, and these presentation is due to my friend and colleague Steve Simon in Oxford University in England. I'll give you a cartoon picture. So imagine we have three particles, and they have an internal degree of freedom. For simplicity, we call it spin. It can either be up or down. Okay, and we label these three particles by whether they're pointing up or their spin is pointing down. And in the language of quantum mechanics, that defines a Hilbert space. The Hilbert space can be rather large. It can be, it has as a number of vectors 2 to the n, where the n is the number of particles. And since we can label all these states, I'm not going to do it here, but you can imagine labeling all the spin configurations, if you would, of all the particles going from n equals 1 to n. Now, and that can be written out as a linear combination. We can write an initial state, and this is just fancy notation to say that we can write down the wave function for the initial state, and it depends on the parameters, how it occupies states in this Hilbert space. Now, it's better to describe the evolution in time. So we put time on the vertical axis, and we allow the system to evolve. And all we do here is just wrap one particle around another. We didn't, change the interaction or do anything fancy. We just braided them around one another. But for non-abelian particles, this actually changes the internal degree of freedom. So I'm going to show you a little picture from a top-down view where all I've done is rotate these particles around each other. And you say, well, they're indistinguishable particles and the configuration looks the same. So what could be changing? But in fact, this internal degree of freedom, let's call it spin for sake of clarity of argument, it actually changes due to this braiding. So this exchange or braid operation actually changes the internal degree of freedom. And that's really powerful because that we can use to store quantum information. So the final state, even though we've just exchanged particles, is different than the initial state. And that's the defining property of non-abelian anyons. There's a unitary matrix. It's a mathematical statement saying we conserve probability. The matrix depends only on the topology of the braid, how we take them around each other. The initial and final state is what matters, not how we get there, okay? And so these matrices don't commute. These unitary transformations don't commute. They're, in the language of mathematical physics, they're called non-abelian representations of the braid group. And very smart mathematicians and physicists developed this theory. It's not something I understand myself, but I tried to implement. And it turns out that there's this branch of physics called topological quantum field theory that makes connection between these abstract concepts and some physical observables that we have in the lab. Okay, so the real idea is why it could be interesting for quantum information is this notion of topological robustness. So I've showed you a very dignified and calm exchange of two particles in the where they just went around each other. But in the real world, what could happen because of noise in the environment, they could be bouncing around and jiggling during that operation. From a viewpoint of topology, it doesn't matter. This very calm and dignified development in time that you see on the left, from the point of view of the braiding operation, is completely equivalent to this noisy, jittery one. Only the final state and the initial state matter. And that's why people, at least in principle, are interested in these from a quantum information perspective, is that it could provide some degree of protection against the decohering aspects of the noisy environment. But that I just wanted to give you a flavor for and why you could be interested in these things. Now, how do we do it really in the lab? And this is what I want to tell you about. We build a two-dimensional electron gas by putting the two-dimensional electron gas at the interface of dissimilar semiconductors. So here I have a cartoon of gallium arsenide, aluminum gallium arsenide heterostructure that's grown by an ultra-high vacuum technique called molecular beam epitaxy. This funny instrument, it doesn't look comprehensible, but it's an ultra-high vacuum chamber where all the atoms have been removed. The vacuum in there is about 10 to the minus 12 torr. Okay, that's 15 orders of magnitude lower than atmospheric pressure. So an atom that comes out of a source can go all the way across the chamber without seeing any other atoms. Okay, there may be another question. Is that true, Dean?
Yeah, there's a question by Gordon Push. To paraphrase, he's commenting on the fact that if space really had only two spatial dimensions, then the Coulomb potential would be logarithmic rather than 1 over r. And so he was wondering if the 1 over r, which comes from the fact that we're really in the full three-dimensional space, whether that's important for the anionic effect.
Right. And so that's a good point and is true. When I mean two-dimensional here, in reality, of course, we live in three-dimensional space. But in the electron systems we're talking about, we have something called size quantization. They're basically confined in a region where the dimensions of the box that they're confined in is comparable to the Fermi wavelength of the particle. And when you have that, you have a discrete spectrum for the z direction. So it's the old particle in a box problem from introductory quantum mechanics. And so when I say an electron system, at least in this case, is two-dimensional, what I mean by that is it can only occupy the lowest quantum state in the z direction. All other z states are frozen out. There's an energy gap, and KT is so low that there's no probability for occupying another z state. So while the particle is essentially free in the plane, it can only occupy one state in z. Now, the Coulomb potential, of course, in this system is still three-dimensional. The field lines go everywhere, and they see the dielectric change in the dielectric properties of the host material. So it is an important consideration. Now, in my system, I can just talk about electrons confined at the hetero interface. Of course, there are 2D materials like graphene and other materials now where they really are kind of an one atomic layer. And the electrons are, if you want, even closer to the strict 2D limit there. But when I say two-dimensional, I mean that there's no degree of freedom for z motion. Okay, so we can build these layers, and here in this high vacuum system, I have to see how I'm going pretty slowly, so I'll have to speed up. But in this ultra high vacuum system, we can build different materials layer by layer, one atomic layer at a time. So in the lower right, you see a cross-sectional TEM image of what's called a superlattice, alternating layers of gallium arsenide and aluminum gallium arsenide. And you can see the scale bar, 50 nanometers down in the lower right. If we make these quantum wells of gallium arsenide skinny enough, the motion really is quantized and effectively two-dimensional, and that's what I mean, okay? I'll try to move along. So now you could say, well, okay, the theorists told you back in the 80s they should be fractionally charged and have fractional statistics. What took so long? Well, the experiments aren't easy, and I can't go into all the details, and a lot of people had to, do some very important experiments, and there had to be a lot of development. But you have to go all the way from growing the heterostructures to making mesoscopic nanoscale devices using clean room techniques, making little devices. And then the devices have to be measured at very low temperature and high magnetic field. And that takes place in dilution refrigerators. So we get near absolute zero and can apply magnetic fields up to 15 Tesla perpendicular to the plane. And, to get all this working and understand all the nuances took a long time. And while the ideas are beautiful in principle, what makes it interesting for me is trying to figure out what actually is needed to make the experiments work. So along this path, you have to go from materials to devices to measurements. Okay, so we want to measure this anionic phase. How do we do it? Well, we developed something called an electronic Fabry-Perot interferometer. Now, interferometry is a way in optics of looking at small changes in phase. You can have exquisite resolution by looking at interference patterns that build up in classical electromagnetics. And what we're using here is sort of the electronic analog of a light interferometer. So what we do is the blue region is the two-dimensional electron gas. These yellow lines that I'm pointing at right now are surface gates. They're electrodes that we use to deplete the electron gas locally in a specific region. And so the pattern that we make defines an interference chamber. We have contacts labeled by S and D for source and drain, in which we can sink and source current through. So these surface gates that we define by electron beam lithography define the interference chamber and the interference path. These little metal electrodes come in close proximity. There's about 300 nanometers between in this opening, and they act as the beam splitters, the electronic analog of a beam splitter. So if I think about it, the current comes in, goes into this first beam splitter, is partially reflected and partially transmitted. Most of the current goes into the interferometer, and then it goes to the second QPC, the second splitter, and we partition off some of the current there. And some of the current backscatters. It goes into this interferometer and creates an interference pattern. Now, the interesting thing is we think of electrons as particles, but it has a wave-like nature. So the current that actually ends up on the drain depends on the interference that takes place inside the interferometer. So the current that makes it out, that's I, depends on the transmission coefficients, that's that T1, T2 squared of these beam splitters. And there's a cross term, an interference term, cosine theta. Now, this theta is not the anionic phase I told you about earlier. It's actually the interference phase. But by building this interferometer, I can take advantage of the wave-like nature of these quasi-particles and look for subtle changes in phase associated with interference. So if I'm dealing with just normal electrons, the phase that develops is called the Aronoff-Bohm phase. It depends on the area of the interferometer and the magnetic field that's propagating through it. And it's periodic in the magnetic flux quantum, H, just a ratio of fundamental constants, H over E. So A is the area of the interferometer, B is the magnetic field that's applied, and I have something that's periodic in that's called the Aronoff-Bohm phase. And that's been seen before in many systems. That's not unique, but we're doing it here in the quantum Hall regime. So I can measure the interference by measuring electrical conductance across the device. And I can operate the device by changing the area by those two T gates. I can squeeze, it's like an accordion. I can make it bigger or smaller by putting voltage on those. Or I can change the magnetic flux through the system by changing the magnetic field perpendicular to it. So I expect the phase, the lines of constant phase or constant conductance, to have negative slope in the BVG plane. So this is a theoretical prediction where we have a 2D color map. The color corresponds to the phase, or if you want to think of it, just the value of conductance. And as I change magnetic field or flux on the x-axis or change voltage on the y-axis, I see these barbershop pole-like behavior. Now, that's what we expect for normal boring old electrons. If we're dealing with anions, this behavior gets modified in significant ways. What happens is if we have anions in the system, that periodicity gets scaled by the effective charge. So I can use the interference to really extract the effective charge of the anyons. And it's also directly proportional to the anionic phase through the number of localized anyons. A little spiral squiggle represents a localized anyons. So imagine I change the number of anyons. One enters or leaves the interference chamber. I should see a glitch, a phase slip, like you might call it noise, in this interference pattern I'm showing you. But if it's not noise and has a regular pattern where we remove quasi-particles, you'll see these glitches, and that's what we're looking for. Okay, so I'm going to have to rush through all of this. Now I'm getting towards the end, but theoretical predictions were made way back in the 90s and elaborated on in the 2000s by many folks, and we're just searching experimentally for this type of behavior. Now, where we come in is in an innovation in the heterostructure and device design. In order to actually probe the 2D electrons here, we have to build a somewhat complicated heterostructure that has ancillary quantum wells in it, meaning extra 2D electron gases. Those are used to screen out some of the effects that aren't, basically just confuse us in our experimental probes. So we have to make complicated devices, but that's a small penalty to pay for being able to probe the anionic statistics in the main quantum well here. Now, I'm gonna, in the interest of time, gonna move quickly, but what we really did was make, instead of one 2D layer, we made 3 of them. We made like a wedding cake of 2-dimensional electron gases. And we used the one on the top and the bottom as sort of utility service 2DEGs to make sure that we can measure the properties in the central one. And that's what we're really after. So our device becomes complicated. We have to have lots of gates on the structure so that we can selectively look at the transport through the main quantum well. So we have a subway system above and below the main quantum well where we can cut off conduction through what we call the screening well, the top one and the bottom one. And then we look at conduction just through the middle one. Now these screening wells are still there and they help us, but we have to have complicated devices in order to look at the interference in a little tiny mesoscopic device in the center. Okay, so the interferometer is still a very small object. Here's a scale bar of 500 nanometers. Here's what it looks like. This is a SEM image of a real device. You can see the gates. There's also a top gate on top, and the interference loop is in here. But the advantage of these 3 layers is we can make the interference device small. That allows high coherence. Remember, quantum mechanics and any wave phenomenon in general relies on coherence to see interference, and that was the real advantage of this design. So if we go to the integer state, this nu equals 1, where 1 electron per flux quantum, we kind of see a textbook example. This is real data now of the interference pattern that the theorists told us we should see. I showed you that a few slides ago. And this is really the modulation in conductance due to interference as we change the magnetic field on the x-axis and the side gate, that plunger gate, on the y-axis. And by looking at the periodicity, both in magnetic field and gate voltage, we can learn something about the charge carriers. And these are bare electrons, okay? But we know the periodicity by some analysis. And the fact that we can make it small made it highly coherent. Now let's go to the fractional state, nu equals 1/3. And again, we can see the interference pattern if we look over this narrow range of magnetic field. And the change in periodicity, I don't have to go through all the math for you, just have to take my word for it. The change in the periodicity is consistent with having charge E/3 quasi-particles. We went from electrons to quasi-particles, and boom, the periodicity changed just in the manner we expected it to be consistent with E/3 quasi-particles. Okay, now what I haven't shown you yet are these phase slips. That's coming next. So we had to go through a few iterations of this experiment, but in 2020, we were able to construct ones that had this lines of constant phase with negative slope as I'm pointing out with the laser pointer, but there are also these discrete slips, phase slips. And it turns out we can analyze those phase slips, and don't have to go through the mathematics for you here, but you may say, well, that's just junk, you know, it's electrical noise in your measurements. It doesn't look so good to me. But if you do the analysis and try to repeat it many times, you see that the phase slips, these little glitches in the data, correspond to the introduction or removal of one fractionally charged quasiparticle with a statistical phase of 2 pi over 3. And we can analyze that phase slip. The values that come out are completely consistent with the average phase slip, and we've done this many times in different samples and done the analysis. The phase slip is minus 2 pi times 0.31 plus or minus the experimental limits on the ability to measure it of plus minus 0.04. And so remember, that's pretty close to 0.33. And remember, theory told us that the anionic phase should be 2 pi over 3. That's what we get in experiment. The reason for the minus sign is that we're removing quasiparticles in the way we do it. So there's a loss, removal of a quasiparticle, and that gives you the minus sign. So we took this as experimental evidence that we could actually measure quasiparticles' charge and phase. And I think this was, there were other experiments being done and some other ones that are also very good at exposing this type of physics. But this was one of the early ones that gave you really strong evidence that we were looking at fractionally particles, anyons with fractional statistics and charge. We've gone on to sharpen those experiments. I don't want to go into that in the interest of time, but we can refine the experiments. And just so you may have thought that the original data looked a little wishy-washy, now you can see in their refined devices and measurements that these phase slips are very discrete. There's one before a phase and after, and this discontinuous phase slip is, as far as we can tell, can be associated with the removal of individual anions. And so, as I said, to show that they were fractionally charged took about 15 years of development of quantum shot noise measurement. And now it's about 40 years after your initial theoretical proposal that they would have fractional statistics that were able to say that in these two-dimensional electron systems, we really do have particles, excitations with fractional charge and fractional statistics. So in the interest of time, I'm just not going to go into this. We've extended it to other fractions, more complicated cases. This is not a one-trick pony. We can use the technique on other phases of matter. My great hope is that people working on other quantum systems, be it in graphene, which is already being utilized, but the transition metal dichalcogenized 2D materials, that this technique will be applicable there as well. We've shown in the past year that you can do it for more complex fractions. So, and there were challenges associated with this extension, as the theorists told us there would be, but nevertheless, the continued improvement of the materials and the experimental techniques allows us to basically probe some pretty unusual aspects of quantum mechanics that wouldn't be able to be seen otherwise. So just to summarize, I'm going to go on, that we've been able to develop these novel header structures and devices to overcome some of the challenges associated with doing interferometry. And, we built on the experimental progress of other groups and we learned from them. But with these new interferometers, we can really see directly the fact that we have fractional statistics and fractional charge. And I think that's pretty cool for the field and pretty cool for the larger community of condensed matter physicists who want to probe this type of behavior in other systems. And just to let you know that there have been other experiments done by other groups. There's anion colliders, the analog of the particle accelerator and collider. We have those for anions, where you bring anions into an interaction regime and see how they scatter out. That is work done, really beautiful work done by a group in Paris, by Glenn Balfev and others. And by looking at the correlations in the noise, they're able to see the anionic statistics as well. So there's lots of really cool work out there by other groups that I don't want to give short shrift, but in the interest of time, I'll just summarize here. So I hope I've told you enough that you are at least not disbelieving that we can have excitations in nature where the indistinguishable particles actually have fractionalized quantized values. And this is a recent development and just shows that we can continue to learn about fundamental quantum mechanical properties even 100 years after your initial formulation of quantum mechanics. So thank you very much.
Michael, that was a beautiful talk. So thanks so much, and
Yeah,
a great presentation in physics. In the interest of time, we can take maybe one more question. So if you have a question, go ahead, put that into the question and answer dialog box.
Yeah, you can also feel free to email me later if you have questions you didn't think of. Just mmanfra@purdue.edu. So hopefully I'd be able to answer any questions you may have.
All right. So while we're waiting, maybe I can ask a question. So the non-abelian case. So what challenges are there for that?
We're certainly working on that, and there are many systems, proposed systems that may host excitation, non-abelian excitations, and that's a lot of my work with Microsoft and the topological superconductor systems that we look at there. In the fractional quantum Hall effect, certain states are abelian, but some are expected to be non-abelian, like the nu equals 5/2 state. That state is a little different than the ones I've described to you here, the Laughlin-like states. The Laughlin states all have an odd denominator and are believed to be abelian. The 5/2 state turns out that it may be something akin to Bose-Einstein condensation, or Bose-Einstein condensation, a BCS-like paradigm. I said the wrong word, sorry, of these objects, composite fermions, and that give rise to the quantization at 5/2. And if that is true, then theory tells us that the excitations will have non-abelian statistics. Now, what's hard about it is that these non-abelian states are very fragile. They have small energy gaps. They're very sensitive to disorder. So you have to make the samples very, very clean. And all this edge state physics I talked about, interference, depends critically on the charge of the quasi-particle, the velocity of the edge states. All these real material parameters come in to play when deciding how robust the features will be. And so we have ideas. We're trying to make them right now, and there's many groups working on it. I am confident that we will have solid proof that the fractional Hall effect at 5/2 has non-abelian braiding statistics in the not too distant future. And there are experimental out there that already suggest that. The quantized thermal conductivity measurements of the Heiblin group at Weizmann. I mean, there's lots of things that are in. Bob Willett from Bell Labs has interference experiments. There's lots of indicators out there that already point to this. It's just tricky because of the small energy scales associated with these non-abelian states.
All right.
Graphene may help there too, because they have much larger energy gaps in graphene. So Andrea Young at University of California, Santa Barbara may be able to do interference with 5/2 as well.
Yeah, so related to that, Yanzhou Ma makes a question. Are there potential applications of fractional quantum Hall effect, like for quantum computers?
Yeah, as I actually work on trying to build practical quantum computers, I think fractional quantum Hall physics, at least in the gallium arsenide system, is not likely to be. It's a great proving ground for basic ideas because it's so clean and so well developed, and we have such fine control over it. The energy scales are quite small. All energy scales are below Kelvin, and so and it's a highly correlated system. So having predictive power about having multiple, there's no doubt you can build individual qubits, but building a lot of them and having them all look the same and perform the same, I think, is a challenge. Now, certainly that motivates some of the work we do on other hybrid systems, the superconductor semiconductor systems, where non-abelian excitations or at least defects are predicted to exist. And we have evidence of that. That's the work with Microsoft Quantum. So there are ways which I think will be topological degrees of freedom will be used for quantum computing. I certainly am working on that. The fractional quantum Hall effect in gallium arsenide is a little, to make a practical technology, I think it's a little, it just doesn't have the energy scales. But if we can prove these ideas in gallium arsenide, that doesn't mean that other materials won't come along, be it graphene or TDMs or, all sorts of other materials that may have much larger energy scales. And then all the concerns I mentioned have to be reevaluated. It could be practical. So for the system I work on, it's a little tricky, but it doesn't mean it won't happen. That's why I'm working on it.
Okay, great. So Michael, thanks again so much for your time and the wonderful presentation and answering the questions. That will stop the recording now.
Thanks for the good question.